to our viewers. You are welcome to today's episode in the continuing series on the laws of physical science. Today, we are going to consider Newton's law of universal gravitation, how it relates to objects in the universe, the distance between the objects, and the force of attraction between and among objects. And then we are going to go further by looking at Archimedes principles, which is a principle of fluid mechanics that involves the displacement of water or weight from a fluid. We are going to look at the applications, industrial applications of Archimedes principles, and then we are going to round up today's episode with the consideration of the law of conservation of energy, which is a law that connects all areas of physical sciences, not just the mechanical aspects. We can talk about potential energy, kinetic energy, sound energy, all forms of energy, where you have unison in engineering and physical principles. I believe you are going to enjoy today's episode. Thank you very much. Newton's law of universal gravitation. We have abbreviated this law as NLUG. N for Newton, L for the law, U for universal, and G for gravitation. So that subsequently, when we use NLUG, we are referring to Newton's law of universal gravitation. So we can see this sketch, which illustrates Newton's law of universal gravitation. The key words there are universal and gravitation. So this law deals with gravitation, and it talks about objects in the universe that are attracted to one another. Here we have used two objects. Object 1 having mass m1 and object 2 having mass m2. So we can see the force of attraction between there is attraction between the two forces. You can see the force of attraction is denoted by F. And we can see the distance between the two objects, between object 1 and object 2. We have drawn it based on their center of gravity. It could have been from air to air. Okay? So the distance between them is denoted by r. So Newton's law of universal gravitation connects the masses of the objects 1 and object 2. It connects the masses with the force of attraction between the two objects, and then the distance between the two objects. These are the results that have been measured experimentally, and they have been validated analytically, mathematically. So what the law says is that the force of attraction between the object 1 and object 2 is directly proportional to the product of their masses. The mass of m1 times the mass of m2, 1. 2, that the force of attraction between object 1 and object 2 is inversely proportional to the distance between the two objects. Well, when we talk about universal gravitation, we are talking of the entire universe, as it involves all objects in the universe, the planets, the sun, the moon, and so on and so forth, especially heavy objects. That's what the gravitation relates to. So, using the two relations, this is a direct proportionality, and this is an inverse proportionality. We can connect the two proportionalities by saying F is equal to G m1 m2 all over R2. where this G is a constant. And this constant has been measured, and the constant is called the universal gravitational constant. It has been measured experimentally, and the value is 6.67430 times 10 raised to the power minus 11, and this is the unit. M raised to the power 3, kg raised to the power minus 1, s raised to the power minus 2. Of course, we are talking of unit of distance, meters, kilograms, unit of mass, and s, the units of time. So the force of attraction between any two objects in the universe, wherever the two objects are, especially objects with large masses, can be denoted by F is G all over. That's the force of attraction. Indirectly, we can talk about the force of attraction between the stick that I'm holding and this board. Okay, even though that force is negligible, we may not easily see it. It cannot easily be measured, but there is a force of attraction. There is a force of attraction between two cars parked either together or far away from themselves. There is a force of attraction between two walls of a building. There is a force of attraction, and so on and so between two buildings, between two planes, and so on and so forth. So that is what Newton's law of universal gravitation, that's what it all is all about. Connecting the masses of the two objects with the force of attraction between them and the distance. So having discussed Newton's law of universal gravitation, we now move to Archimedes' principle. Archimedes' principle is a principle in mechanics too, but here we are dealing mainly with fluid mechanics. When we talk about fluid mechanics, you are talking about mechanics of liquids and gases. Because when you talk about mechanics generally, and when you talk about matter can exist as solid, it can exist as liquid, and it can exist as gas. So there is general mechanics that discusses dynamics and statics in general, and then there are specific mechanics, principles for fluids, and that's why you also have a separate branch of mechanics that is called fluid mechanics, which deals particularly with liquids and gases. And in fact, there is also another one within the fluid mechanics that's called hydrodynamics. That one deals specifically with principles relating to fluid, to water, not fluid generally, not gases, to liquids generally. So Archimedes' principle is a very interesting principle, and it has an history. It's actually due to a great scientist called Archimedes of Syracuse, who was born around 287 BCE, before the Common Era, and he died around 212 BCE. He was a notable scientist in Syracuse, and history made us to understand how this principle came about. How did it come about? The story reads that the king of Syracuse wanted to make a crown made entirely of gold. And he gave the gold to the blacksmith to turn into the crown. But after they are finished, he wanted to know whether the blacksmith cheated him or not. And then he called Archimedes, who was a notable scientist, natural philosopher, and thinker of that era. And okay, I'm going to give you this work to do, this assignment, this task. I want you to help me determine whether this blacksmith added some other elements to the gold, whether he diluted it with silver or bronze or some other elements, because I gave him the task of bringing forth a crown made so and I gave him gold so that he could make the crown. Then Archimedes thought about it for a while. He couldn't find a leeway, a solution easily, and that leads us to a very important principle in science generally and in nature, the concept of intuition. That when you are trying to solve a problem, you cannot solve the problem, just let it go. You can sleep over it. One day, sometimes, in the course of your normal duties or whatever, even when you are not thinking about the problem, the solution will come. That was exactly what happened in the case of Archimedes of Syracuse. So one day, without even thinking about the problem, because he was at a corner, he was at a crossroad, he didn't know how to go about it, so he was just baffling. He was having his breath baffling, and then he just observed that as he dived into the bathtub, some element, volume of water is displayed from that bathtub. And it just occurred to him that, oh, I have actually found the solution. And he cried out and said, Eureka, I have got it. In fact, the history tells us that he actually came out from the bathtub, from the bedroom, and went to the street naked. Because he was so excited, because he had thought about how to solve the problem, he couldn't find the solution. And here he was, that he was able to just solve the problem without thinking about it, just by performing a natural activity. So the principle, we can see what we have used to represent the bathtub, and then we can see the water inside the bathtub, and we can see an object here. The principle is relevant to the situation in which the object is partially immersed in this water. You can see that, you can still see some parts of the object, they are not in the water, some parts are in the water. So it applies to whether some parts are inside the water, whether the partial immersion or full immersion. In this case, you can see the object is totally inside the water. And then what he observed when he jumped into the water, that immediately he jumped into the water, as the object moves in, as he jumps into the water, a certain volume of water is displayed. So there is a force which is called the upthrust, a negative, a force, a counter force, which we can still relate with Newton's law of third law of motion. Action and reaction are equal and opposite. So you can see the force that takes him inside, then there is a force that brings out the water out. That force is called the upthrust. So we can see the same here in the case of partial immersion, and in the case of full immersion, you can see the same. So irrespective of whether there is partial immersion or there is full immersion, Archimedes' principle applies. And we can see from there, we can look at how the equation, how it works, that when you jump into the water, or an object is immersed into the water partially or fully, it displaces. There is an upthrust. There is an upthrust, a force that brings water out, such that that force is equal to the weight of the displayed fluid. It looks commonsensical, but at that time it was not like that, because it was not as simple and it was not as easy to perceive as we are doing it now. So, but we know that it looks common. It's like you take a bucket of water and you throw a stone inside the water, you discover that some water comes out, volume of water comes out from the bucket. So that is what Archimedes' principle is trying to explain. So the force is equal to the weight of displayed fluid. And of course, we know that the weight is mathematically and physically can be described as MA. Okay, where the M is the mass and A is the acceleration. So, but we are talking about fluid now, talking of water. So the mass can be described as the density of the water times the volume of the water. So rho V is the mass, and the acceleration in this case is the acceleration due to gravity. In an earlier episode, we explained the concept of gravity, the natural gravitation acceleration that is available on the Earth. So can see that the force is actually minus rho Vg. The minus, we are using that in the sense that the force is opposite to it, just like we mentioned in the case of Newton's third law of motion, action and reaction. The force is in the opposite direction. So you can have minus rho Vg, where rho is the density and V is the volume of fluid. So that's Archimedes' principle. A very important principle in fluid mechanics, and it has a lot of applications in real life. We just want to consider two basic applications which are, popular. The first one, we can talk about the nautical or marine engineering. That is engineering of the sea that involves equipment, devices, design, construction, involving devices on water, moving on water, and so on and so forth. So that's nautical marine engineering. And that is applicable to design of ships, because this principle takes note in the course of design of the ships. This principle is taken into consideration in the various design calculations, so that the ship does not sink. There is water. The ship is on the water, and it has to be moving through the water. So Archimedes' principle is taken care of in there. The same thing with respect to aeronautical engineering. When we talk about aircraft motion, we see the plane, the helicopter, and even drone, all these heavenly objects moving here and there. So the principle in the design can be traced to Archimedes' principle. Of course, there are other principles of fluid mechanics that are taken into play. Now, there's Stokes equations and so on, but those ones are more advanced principles. So, aeronautical engineering, Archimedes' principle is taken care of. In nautical engineering, design of ships, and so on, Archimedes' principle is taken care of. Then we want to now look at the principle of conservation of energy. The principle of conservation of energy is still related to mechanics that we are considering, but it also relates to other areas that are not necessarily mechanical. So what the principle of conservation of energy, what it just canvases for, is that when you have a closed system, wherever, and you have energy being converted from one form to the other, and so on and so forth, provided until you get to the end, provided you have a closed system, within that system, the total amount of energy in the system is constant. Energy can be converted from one form to the other, but it is not destroyed. So that is the principle. So if I have a system that involves all these forms of energy, potential energy, kinetic energy, heat energy, light energy, sound energy, chemical energy, and nuclear energy, and we know that the system involves all this energy, the total sum is constant. Energy can never be destroyed, but it can be converted from one form to the other. And we can look at the various forms of energy. We can see this is potential energy. For instance, you have an object on a table, like the stick that I'm holding now. If I throw it down as it is here in the air, it possesses the kinetic, the potential. There is potential energy here. The potential, the ability to move, is stored energy somewhere. But by the time it's released, it goes down. The potential energy is released. Gradually, the kinetic energy increases and so on until it gets to the floor. So we have the potential energy and kinetic energy. That one is the energy whenever there is motion, then kinetic energy is applied. Then heat energy, wherever heat is involved, like we put water in a pot or in a kettle, and we subject it, we put on the stove, and then it's the discover that it is boiling, it is heat energy that is generated. And then we can talk about light energy in the sense that the energy that brings illumination to an environment, to a room, and so on and so forth. We can talk about sound energy. Maybe you can talk about the alarm clock, alarm system, So you have one form of energy being converted to sound. So that's why you have the sound energy. Then you can talk about chemical energy. A classical example is when you look at the battery of a transistor radio. It stores chemical energy, but it later converts by the time to another form of energy. You can hear sound, bring light, and so on and so forth. Then you have nuclear energy. This one relates to nuclear fission, nuclear power, reactors, and so on and so forth. I believe you have enjoyed today's episode. We hope that you are going to join us in the next episode, where we are still going to continue examining some of the laws of physical science. And we have one of the laws that we are going to look into, the law of thermodynamics. You have the zeroth law, you have the first law, you have the second law, and the third law of thermodynamics, which deals with the mechanics of heat phenomena. Mechanics that involves heat specifically. It's a specific area of science that deals with that. And we are going to look at the basic laws that govern the mechanics of heat. Thank you very much. You are welcome.